Picture this: a universe so young and violent that atoms as we know them couldn't even exist yet. A cosmic cauldron where raw energy ruled, and matter was just an afterthought. Now here's the mind-bending question. What happened in those first moments that allowed atoms to emerge from the chaos? The answer isn't just about science, it's the origin story of everything, including you. Every star, every planet, even the air you're breathing right now was forged from those first atoms. But how? Think of the early universe like a pressure cooker set to trillions of degrees. Protons and neutrons were being tossed around like confetti in a hurricane, too hot to stick together. Then, in a fraction of a second, the cosmos cooled just enough for the first atomic nuclei to form. This wasn't just a chemical reaction, it was the universe writing its first recipe, one that would eventually lead to galaxies, life, and you watching this video. By the end of this journey, you'll uncover 30 groundbreaking theories about those first atoms, from the hydrogen that lit up the cosmos to the mysterious forces that shaped them. Some of these ideas will challenge what you thought you knew about reality itself. So, if you're ready to trace matter back to its explosive birth, keep watching. The universe's oldest secrets are about to unfold. Now, let's zoom in on those first critical moments, the cosmic kitchen where the universe cooked up its very first atoms. Picture this: within just 3 minutes after the Big Bang, the entire universe was a nuclear fusion reactor hotter than the core of any star. This is where the Big Bang Nucleosynthesis model comes in. It tells us how protons and neutrons, those tiny building blocks of matter, finally started sticking together instead of bouncing around in a frenzied dance of energy. At that unimaginable temperature, billions of degrees, protons and neutrons were moving too fast to form stable bonds. But as the universe expanded, it cooled just enough for something incredible to happen. Like ingredients settling into a recipe, these particles began combining to form the simplest atomic nuclei, hydrogen and helium. Hydrogen, with its single proton, was the most abundant, while helium took shape as 2 protons and 2 neutrons locked together. But here's the catch: the universe cooled too quickly for anything heavier to form. The density and temperature dropped so fast that elements like carbon or oxygen never stood a chance. It was like trying to bake a cake in an oven that shuts off after 3 minutes. You'll get the basics, but nothing complex. That's why, for millions of years, hydrogen and helium were the only elements in town, setting the stage for everything that came after. This process wasn't random, though. The exact amounts of hydrogen and helium we see today match the predictions of this model almost perfectly, like a cosmic fingerprint left behind from the universe's earliest moments. And that's what makes the Big Bang Nucleosynthesis model one of the most rock-solid theories in all of cosmology. But don't get too comfortable, because next we'll explore why hydrogen didn't just dominate the early universe, it became its very foundation. Now let's talk about the universe's favorite element, hydrogen. If the early cosmos had a mascot, it would be this simplest of atoms. With just 1 proton and 1 electron, hydrogen was like the blank canvas of the universe, the starting point for everything that followed. Here's why it dominated the scene. In those first few minutes after the Big Bang, protons outnumbered neutrons by about 7 to 1. And since hydrogen is just a lone proton with an electron, it had a massive head start. Helium needed 2 protons and 2 neutrons to form, which was trickier in the fast-cooling universe. So hydrogen became the cosmic heavyweight, making up roughly 75% of all normal matter by mass. But hydrogen didn't just sit around, it got to work. Hundreds of millions of years later, during cosmic recombination, hydrogen atoms finally captured electrons, turning the foggy plasma of the early universe into transparent gas. This was the moment light could travel freely, creating the cosmic microwave background we detect today. And here's the real kicker: hydrogen's simplicity made it the ultimate building block. Gravity pulled these atoms together into vast clouds, which collapsed to form the first stars and galaxies. Without hydrogen's abundance, the universe would have stayed dark and empty. Every star, every planet, even you, all owe their existence to this humble atom. But don't think hydrogen's story ends there. Next, we'll see how its partner in crime, helium, carved out its own cosmic legacy. Now, let's shift our focus to hydrogen's quieter but equally important sibling, helium. While hydrogen stole the spotlight with its sheer abundance, helium played a crucial supporting role in shaping the early universe. Here's how helium made its mark. In the first few minutes after the Big Bang, the universe was still hot enough for nuclear fusion to occur. Protons and neutrons collided, forming deuterium, and then quickly fused into helium-4. This process locked up nearly all the available neutrons, leaving helium to claim about 25% of the universe's atomic mass. What made helium special was its stability. Unlike hydrogen, which is reactive and eager to bond, helium is a noble gas content to stay solitary. Its tightly bound nucleus of 2 protons and 2 neutrons made it incredibly resistant to further fusion or decay. This stability meant that once helium formed, it stuck around, becoming a permanent fixture in the cosmic inventory. But here's the interesting contrast. While hydrogen's reactivity allowed it to form molecules and eventually stars, helium's inert nature meant it mostly stayed as individual atoms. This difference had huge consequences. Hydrogen became the fuel for stars, while helium often just watched from the sidelines until later, when stars began fusing hydrogen into even more helium in their cores. So while hydrogen was the star of the show, helium was the reliable understudy, quietly shaping the universe in its own way. Next, we'll tackle a cosmic mystery: why the amount of lithium we see today doesn't match what the Big Bang predicts. Now, let's turn our attention to a cosmic puzzle that has left scientists scratching their heads: the mystery of lithium. According to the Big Bang theory, there should be a specific amount of lithium-7 scattered across the universe. But when astronomers measure it today, the numbers just don't add up. The observed levels are way lower than predicted, and no one's entirely sure why. This discrepancy is known as the Lithium Problem, and it's a big deal because it challenges our understanding of the early universe. If the math behind the Big Bang is correct, lithium-7 should be about 3 times more abundant than what we actually see. So where did it go? One possibility is that our measurements are off. Maybe lithium is hiding in places we haven't looked yet, like inside stars or in hard-to-detect cosmic dust. But even accounting for that, the gap remains too wide to ignore. Another idea points to exotic physics, something beyond our current models. Perhaps unknown particles or forces interacted with lithium in the early universe, breaking it down or transforming it into other elements. Some theories even suggest that dark matter could have played a role, subtly altering nuclear reactions in ways we don't yet understand. Then there's the chance that our predictions are based on incomplete data. The Big Bang model relies on precise conditions: temperature, density, and particle interactions. And if any of those were slightly different, it could explain the lithium shortage. Whatever the answer, this puzzle reminds us that the universe still holds secrets. The lithium problem isn't just about one element, it's a clue that could lead us to new physics or reshape our cosmic origin story. Next, we'll explore how deuterium, a heavier form of hydrogen, acts as a cosmic thermometer, helping scientists measure the density of the universe. Now, shifting our cosmic lens, let's zoom in on deuterium, hydrogen's heavier cousin, and its surprising role as a universe-wide thermometer. Unlike the elusive lithium we just discussed, deuterium's abundance is a goldmine for scientists because it acts like a fingerprint of the early universe's density. Here's why it's so special. Deuterium, or heavy hydrogen, forms when a proton and neutron bind together in the intense heat of the Big Bang. But here's the catch: it's incredibly delicate. Even slight changes in the universe's early conditions, like temperature or particle density, would have dramatically altered how much deuterium survived. Think of it like a cosmic seesaw: too dense, and nuclear reactions would have destroyed most of it; too sparse, and not enough would have formed in the first place. This sensitivity makes deuterium a perfect measuring stick. By comparing the amount of deuterium we see today with predictions from Big Bang models, scientists can backtrack to calculate the universe's density during those first critical minutes. The numbers line up remarkably well, giving us confidence in our understanding of cosmic expansion. But deuterium's story doesn't end there. It also hints at how matter clumped together over time. Since stars fused deuterium into helium, regions with less deuterium likely hosted more star formation, while pristine clouds preserve it like a time capsule. This tiny atom, often overshadowed by its lighter sibling hydrogen, quietly holds the keys to mapping the universe's evolution. Up next, we'll tackle another cosmic mismatch: the curious case of missing helium-3, and why this rare isotope might hold clues to stellar secrets. Now, let's unravel another cosmic mystery: helium-3, the lighter and far rarer sibling of helium-4. While helium-4 makes up about a quarter of the universe's atomic mass, helium-3 is astonishingly scarce, and its absence has left scientists scratching their heads. Here's the puzzle. According to Big Bang Nucleosynthesis models, helium-3 should be more abundant than what we observe today. So where did it all go? The answer might lie in the fiery hearts of stars. Unlike helium-4, which is incredibly stable, helium-3 is more reactive. Over billions of years, stars could have burned through much of it, fusing it into heavier elements like carbon and oxygen. But there's another twist. Some helium-3 might have been destroyed in the turbulent environments of supernova, or even ejected into interstellar space, where it became too diffused to detect easily. This means the helium-3 we do see today could be just a tiny fraction of what once existed, a cosmic relic hiding in plain sight. Interestingly, helium-3 isn't just missing in space. Even here on Earth, it's vanishingly rare, found mostly in natural gas reserves or as a byproduct of nuclear decay. Its scarcity makes it a valuable resource with potential uses in futuristic technologies like fusion energy. So, while helium-3 might be the universe's shyest isotope, its elusive nature tells a bigger story, one of stellar alchemy and the relentless transformation of matter over cosmic time. Up next, we'll explore how uneven densities in the early universe could have created pockets of unique atomic chemistry. Now, shifting our gaze to the cosmic tapestry itself, let's consider a fascinating twist in the story of the universe's first atoms. What if they weren't spread evenly at all? This brings us to the theory of inhomogeneous nucleosynthesis, the idea that the early universe wasn't a smooth soup of matter, but instead a patchwork of dense and sparse regions. Imagine a pot of boiling water with bubbles rising unevenly, some areas hotter and more active, others cooler and quieter. These density fluctuations, tiny ripples in the fabric of space-time, could have dramatically altered how atoms formed. In denser pockets, nuclear reactions might have raced ahead, producing more helium or even trace amounts of lithium, while sparser regions lagged behind, leaving behind mostly hydrogen. Over time, these irregularities could have snowballed into the vast cosmic web we see today, a sprawling network of galaxies and voids, echoing the unevenness of the universe's infancy. What's truly mind-bending is that these ancient density variations might still be visible in the cosmic microwave background, the faint afterglow of the Big Bang. Subtle temperature differences in this radiation could be the fingerprints of those early imbalances, clues to how atoms clustered before stars or galaxies even existed. And here's the kicker: this theory doesn't just explain atom distribution. It could also solve puzzles like the Lithium Problem or helium-3 scarcity, suggesting that local conditions, not just universal laws, shaped the elements we see. Up next, we'll dive into how the universe's primordial soup of particles cooled into the building blocks of matter, a story of quarks, gluons, and the birth of protons and neutrons. Now, let's rewind the cosmic clock even further back to a time when the universe was so hot and dense that even protons and neutrons couldn't hold themselves together. Picture a seething ocean of raw ingredients where quarks and gluons, the fundamental particles that make up matter, roamed freely in a state known as quark-gluon plasma. This was the universe's ultimate particle soup, a chaotic frenzy where nothing could stay bound for long. But as the cosmos expanded and cooled, something remarkable happened. Like water freezing into ice, this plasma underwent a dramatic transformation. Quarks and gluons, which had been zipping around independently, suddenly began to stick together, pulled by the strong nuclear force. Think of it like a crowd of people in a bustling market suddenly forming into small, tight-knit groups. These groups, they were the first protons and neutrons, the building blocks of every atom in existence. The exact moment this happened is mind-blowing. Just microseconds after the Big Bang, when the temperature dropped to around 2 trillion degrees. That's when the universe crossed a critical threshold, allowing quarks to pair up in threesomes. 2 up quarks and 1 down quark formed a proton, while 2 down quarks and 1 up quark made a neutron. Gluons, the glue particles, held them together, creating stability where there was once chaos. What's even wilder is that this process wasn't perfect. Some quarks might have briefly paired into exotic combinations before settling into protons and neutrons, like dancers switching partners before finding their perfect match. And just like that, the universe went from a featureless plasma to a place with structure, setting the stage for everything that followed, from the first hydrogen atoms to the stars and galaxies we see today. Up next, we'll explore why free neutrons were such a rare commodity in the early universe, and how their scarcity shaped the cosmic recipe for matter. Now, let's tackle a cosmic puzzle that shaped the universe's atomic inventory, the neutron bottleneck. Unlike protons, which stuck around as stable building blocks, free neutrons were the elusive loners of the early cosmos. Here's why they were so rare. Neutrons, left to their own devices, have a serious expiration date. They decay into protons in just under 15 minutes. That might sound like a long time in human terms, but in the universe's first few minutes, it was a blink. Imagine trying to gather sand in a sieve. That's how hard it was to keep neutrons around long enough to fuse into heavier elements. This instability created a cosmic traffic jam. For atoms heavier than helium to form, neutrons had to team up with protons quickly before they vanished. But in the early universe's extreme heat, most neutrons were too energetic to bond easily. It wasn't until things cooled down slightly, around the 2-minute mark, that some neutrons could latch onto protons, forming deuterium, the first stepping stone toward helium. By the time the universe was cool enough for more complex fusion, nearly 80% of the original free neutrons had already decayed. That left just enough to cook up helium-4, but not much else. This scarcity is why the early universe was dominated by hydrogen and helium, with only trace amounts of lithium, a cosmic recipe that set the stage for everything to come. Next up, we'll dive into how ghostly particles called neutrinos might have secretly influenced this delicate nuclear dance. Now, let's turn our attention to the universe's most elusive spectators, neutrinos. These ghostly particles, born in the fiery chaos of the Big Bang, barely interact with matter, yet they might have played a quiet but crucial role in shaping the first atoms. Neutrinos are so light and fast that trillions pass through your body every second without a trace. In the early universe, they were everywhere, outnumbering protons and neutrons by over 1 billion to 1. But here's the twist. Even though they rarely collide with other particles, their sheer abundance meant they could subtly tweak the rates of nuclear reactions during nucleosynthesis. Think of it like this. Imagine a crowded room where everyone's whispering. You might not hear any single voice, but the combined effect changes the atmosphere. Similarly, neutrinos' weak interactions slightly altered the energy balance in the primordial soup, speeding up or slowing down how quickly protons and neutrons fused. This could explain tiny discrepancies in the observed amounts of helium and deuterium compared to theoretical predictions. What's even wilder, the cosmic neutrino background, a relic sea of these particles still drifting through space today, holds clues about these early moments. By studying it, scientists might one day decode how neutrinos quietly nudged the universe's first atomic recipe. Up next, we'll venture into darker territory, where mysterious particles we've never seen could have left their mark on creation itself. Now, let's step into the shadows of the cosmos, where an invisible player might have quietly influenced the birth of the first atoms: dark matter. The mysterious substance that makes up most of the universe's matter could have had a hidden hand in shaping those primordial elements, even though we can't see its fingerprints today. Here's the intriguing idea. While dark matter doesn't interact with light or ordinary matter the way atoms do, some theories suggest certain types of dark matter particles might have briefly collided with protons and neutrons in the early universe. These rare interactions could have acted like cosmic matchmakers, nudging nuclear reactions just enough to alter the amounts of hydrogen, helium, and lithium that formed. Imagine dark matter as a stealthy backstage crew at a concert. You don't see them, but their work behind the scenes affects the entire show. If even a tiny fraction of dark matter particles helped protons and neutrons fuse faster or slower, it could explain why some of our predictions about early atom abundances don't quite match observations. The wildest part, if dark matter did play this role, it would have vanished without a trace once the universe cooled, leaving no direct evidence, just subtle inconsistencies in the atomic recipe we're still trying to decode. Scientists are now exploring whether exotic dark matter candidates, like weakly interacting massive particles or actions, could fit this cosmic puzzle. Up next, we'll tackle one of the universe's greatest mysteries: why matter won out over antimatter, allowing atoms and us to exist at all. Now, let's unravel one of the most baffling puzzles in cosmology: why the universe didn't vanish in a flash of light moments after the Big Bang. Here's the mystery: when matter and antimatter meet, they annihilate each other, leaving behind pure energy. So why did matter, the stuff of stars, planets, and us, end up dominating the cosmos? The answer lies in a tiny cosmic imbalance called baryon asymmetry. For every billion antimatter particles created in the early universe, there were roughly 1,000,000,001 matter particles. That 1 in a billion difference is why anything exists at all. But what caused that imbalance? Enter CP violation, a subtle quirk in the laws of physics. Normally, the universe treats matter and antimatter symmetrically like a perfect mirror. But certain rare particle interactions, like those involving quarks, violate this symmetry, favoring matter just enough to tip the scales. Russian physicist Andrei Sakharov laid out 3 conditions needed for matter to win out. First, the universe had to be out of thermal equilibrium, meaning particles couldn't just bounce back to balance. Second, there had to be processes that didn't treat matter and antimatter equally. That's where CP violation comes in. And third, these interactions had to violate baryon number, a rule that normally keeps matter and antimatter in lockstep. Without these conditions, the universe would have been left with nothing but radiation. Instead, that razor-thin margin of surviving matter became the atoms that built everything we see today. Next, we'll explore how the universe's explosive infancy cosmic inflation shaped the distribution of those first atoms across the cosmos. Now, let's zoom out and see how the universe's explosive growth spurt shaped the fate of those first atoms. Picture this: in less than a blink of an eye after the Big Bang, the cosmos underwent a mind-bending expansion called cosmic inflation, stretching from smaller than an atom to nearly the size of a grapefruit. This wasn't just fast, it was faster than the speed of light, and it left a lasting mark on how atoms were scattered across space. Here's the key takeaway. Inflation didn't just stretch the universe, it ironed it out. Before inflation, the cosmos might have been a chaotic jumble of hot, dense particles. But that sudden expansion smoothed things out, leaving hydrogen and helium atoms spread with near-perfect uniformity. That's why today, no matter where you look in the universe, you'll find roughly the same mix of these primordial elements. But there's a twist. Inflation also planted the seeds for everything we see today. Tiny quantum fluctuations, think of them as microscopic wrinkles in spacetime, got stretched to enormous scales during inflation. These became the faint density variations that later attracted matter, forming the first clumps that would grow into galaxies. So while the universe looks smooth on large scales, those subtle imperfections were the blueprint for all structure, from stars to superclusters. Without inflation, the cosmos might have remained a featureless soup of atoms. Instead, it gave us both uniformity and variety, a cosmic canvas where the first atoms could eventually light up the darkness. Now, let's take a closer look at those tiny quantum wrinkles we just mentioned, because they weren't just random noise. They were the universe's first architects. Imagine the infant cosmos as a quiet pond, and these fluctuations were like the faintest ripples on its surface. But here's the thing, during inflation, those ripples didn't fade away. They got stretched across space, becoming the subtle hills and valleys in the density of matter. Where the ripples were slightly denser, gravity got to work. Hydrogen and helium atoms were drawn to these spots like iron filings to a magnet. Over billions of years, these tiny overdensities grew into the seeds of galaxies and stars. Without them, the universe might have stayed a perfectly smooth and perfectly boring sea of atoms. But why quantum fluctuations? At the smallest scales, particles pop in and out of existence thanks to Heisenberg's uncertainty principle. In the frantic early universe, these fleeting jitters got frozen into the fabric of spacetime during inflation. It's wild to think that the grand structures we see today, spiral galaxies, towering nebulae, even our own solar system, trace back to these subatomic tremors. So next time you gaze at the night sky, remember, the stars aren't just scattered randomly, they're the grown-up versions of quantum whispers from the dawn of time. Now let's step into a pivotal moment in cosmic history, when atoms stopped being lonely and started forming the very first molecules. Picture this, the universe had cooled down enough for electrons to settle into orbit around nuclei, creating stable hydrogen and helium atoms. But things were about to get more interesting. In the vast, sparse gas clouds of the early cosmos, hydrogen atoms began bumping into each other. Occasionally, two hydrogen atoms would stick together, forming a hydrogen molecule H2. This might seem like a small step, but it was a game changer. Molecular hydrogen could radiate heat more efficiently than single atoms, allowing these gas clouds to cool down and shrink under gravity's pull. Without this cooling effect, those clouds might never have collapsed to ignite the first stars. But hydrogen molecules weren't the only pioneers. Scientists believe helium hydride, He+, was the very first chemical bond in the universe. A fragile pairing of helium and a hydrogen ion, it formed in the harsh conditions of the early cosmos, where ultraviolet light ripped electrons from atoms. While helium hydride was short-lived, its existence marked the dawn of chemistry itself. These first molecules were the unsung heroes of cosmic evolution. They turned diffuse gas into the raw material for stars, setting the stage for everything that followed. So next time you take a deep breath, remember the air you're inhaling traces its origins back to these humble molecular beginnings. Now, let's turn our gaze to the cosmic giants that shaped the universe as we know it. Population 3 stars. These were the first generation of stars, born from nothing but pristine hydrogen and helium, the only elements available in the early cosmos. Unlike modern stars, which are seeded with heavier elements, these ancient behemoths were pure, massive, and incredibly luminous. Inside their scorching cores, hydrogen fused into helium just like in stars today. But because population 3 stars were so massive, some weighing hundreds of times more than our Sun, their furnaces burned hotter and fiercer. This extreme heat allowed them to fuse helium into heavier elements like carbon, oxygen, and even traces of neon. But their true legacy came in their spectacular deaths. When these stars exhausted their fuel, they didn't fade quietly. They exploded as supernova, blasting their newly forged elements into the cosmos. These explosions were so powerful that they fused even heavier atoms like silicon and iron, scattering them across space. For the first time, the universe wasn't just hydrogen and helium. It was enriched with the building blocks of planets, life, and everything we see today. So while population 3 stars lived short, violent lives, their deaths were the universe's first alchemy labs. Without them, the periodic table would be a lot emptier, and so would we. Now, here's something that might surprise you. Oxygen, the element we breathe, doesn't quite add up in the cosmic ledger. According to the predictions of Big Bang Nucleosynthesis and early star models, there shouldn't be as much oxygen in the universe as we actually observe. So why is there so much of it? One leading theory points to those massive population 3 stars we just discussed. These ancient giants didn't just forge carbon and iron. They might have also produced oxygen in ways we're only beginning to understand. Because they burned so hot and died so violently, their supernova could have triggered unusual fusion pathways, churning out far more oxygen than expected. But there's another twist. Some scientists suggest that early stars didn't all behave the same way. A subset of them might have had slower, more prolonged deaths, allowing oxygen to accumulate in greater quantities before being scattered into space. Or perhaps there were entirely different nucleosynthesis processes at play in the early universe, ones we haven't even discovered yet. Whatever the explanation, this oxygen surplus is a cosmic clue, hinting that our understanding of the first stars and their explosive deaths is still incomplete. And that's what makes this anomaly so exciting. It's a puzzle waiting to be solved, one that could rewrite the story of how the universe built its elemental diversity. Now let's shift our focus to another cosmic latecomer, carbon. Unlike hydrogen and helium, which were forged in the universe's fiery infancy, carbon had to wait for the right conditions inside stars. This delay is all thanks to a process called triple alpha fusion, a stellar recipe so precise it's almost like cosmic luck. Here's how it works. First, stars smash together helium nuclei to form beryllium. But beryllium is unstable. It falls apart in a fraction of a second unless another helium nucleus crashes into it at just the right moment. When that happens, voila, carbon is born. This 3-step dance is why carbon didn't show up in significant amounts until later, when the first stars had burned long enough to reach the scorching temperatures and pressures needed to pull it off. What's fascinating is how delicate this balance is. If the strong nuclear force were even slightly weaker, beryllium would vanish before helium could fuse with it, and carbon wouldn't exist. No carbon means no organic molecules, no life as we know it. So while hydrogen and helium dominated the early universe, carbon's belated arrival set the stage for everything that followed. It's a reminder that the cosmos doesn't rush. Some elements take their time, waiting for the perfect conditions to emerge, and when they do, they change everything. Now, let's turn our attention to one of the universe's most fascinating heavyweights, iron. While lighter elements like carbon took time to form, iron stands out for its incredible stability, earning it a special place in cosmic chemistry. Here's why iron is so unique. At its core, iron sits at what scientists call the peak of nuclear binding energy. This means its nucleus is packed together so tightly that it's incredibly hard to break apart or fuse into heavier elements. In fact, fusing iron actually consumes energy instead of releasing it, which is why stars can't burn beyond iron without collapsing under their own weight. But how does iron even get made? The answer lies in the violent deaths of massive stars, supernova. In these explosive final moments, temperatures and pressures skyrocket, allowing lighter elements to slam together and form iron. And when the star finally detonates, it scatters this iron across space, seeding future generations of stars and planets. What's truly mind-blowing is how this process shaped everything that came after. Iron became a cornerstone of planetary cores, including Earth's, and even plays a vital role in our blood. Without supernova forging iron, the chemistry of life as we know it might never have existed. So while iron might seem like just another metal, its cosmic journey from stellar furnaces to the tips of your fingertips reveals just how interconnected the universe really is. Now, let's venture into one of the most speculative yet thrilling ideas about the universe's first atom: strange matter. Picture this: in the extreme conditions just after the Big Bang, ordinary protons and neutrons might not have been the only players. Instead, exotic particles called strange quarks could have briefly dominated, reshaping how atoms formed in those earliest moments. Strange quarks are a hypothetical type of quark, heavier and more unstable than the up and down quarks that make up normal matter. Under unimaginable pressure and heat, these quarks could have clumped together into strangelets, tiny droplets of strange quark matter. If they existed, even for a fleeting instant, they might have acted like cosmic alchemists, transforming the balance of protons and neutrons in ways we can't yet predict. Here's where it gets wild. Some theories suggest that strangelets could have been so stable that they outlasted ordinary matter, potentially seeding pockets of the universe with bizarre, ultra-dense material. If true, this could explain why certain elements or particle ratios don't quite match our expectations from Big Bang nucleosynthesis. Of course, this is all theoretical. No one's ever detected strange matter. But experiments in particle colliders are hunting for clues, and if they find even a trace, it could rewrite our understanding of the universe's first atoms. So while strange matter remains a tantalizing what if, it reminds us just how many mysteries are still waiting to be unraveled in the cosmic story. Now, shifting our gaze to another fascinating frontier, let's consider how supersymmetry, a cornerstone of modern theoretical physics, might have left its mark on the universe's first atoms. Supersymmetry proposes that every known particle has a hidden, heavier superpartner, a shadow twin that could have played a crucial role in the cosmos's infancy. Imagine the early universe as a crowded dance floor where particles and their superpartners whirled together in a high-energy frenzy. These superpartners, like the photino partner to the photon or the squark partner to the quark, could have briefly outnumbered ordinary matter, altering the delicate balance of nuclear reactions during nucleosynthesis. Their presence might have turbocharged particle collisions, creating exotic short-lived elements or even stabilizing rare atomic configurations we no longer see today. Here's the twist: superpartners are thought to be unstable, decaying into lighter particles as the universe cooled. But their fleeting existence could have imprinted subtle anomalies in the abundances of hydrogen, helium, or lithium, hints we're still searching for in cosmic data. Some models suggest these ghostly particles might have even mediated interactions between dark matter and ordinary atoms, weaving unseen threads into the fabric of the early universe. While supersymmetry remains unproven, experiments at the Large Hadron Collider continue to hunt for these elusive partners. If they're found, it wouldn't just solve puzzles about the universe's first atoms, it could unlock entire new chapters in physics. So as we peer back into those primordial moments, supersymmetry reminds us that the cosmos might have once been far richer and far stranger than we ever imagined. Now let's turn our attention to another intriguing puzzle, the gravitino problem. These hypothetical particles, born from theories of supergravity, could have thrown a wrench into the delicate machinery of early atom formation. Gravitinos are thought to be the superpartners of gravitons, the hypothetical carriers of gravity, and if they existed in the early universe, their presence might have been anything but subtle. Picture this: as the universe cooled, gravitinos being incredibly massive could have decayed unevenly, releasing energy in ways that disrupted the smooth dance of protons and neutrons. This disruption might have skewed the ratios of hydrogen and helium we see today, leaving behind a cosmic fingerprint we're still trying to decode. Some theories suggest gravitinos could have even overproduced certain elements, creating pockets of unexpected abundance or scarcity in the primordial soup. But here's the catch: if gravitinos were too plentiful, their decays could have injected so much energy into the young cosmos that they'd wipe out the carefully balanced products of nucleosynthesis altogether. This gravitino problem forces physicists to walk a tightrope, fine-tuning models to ensure these particles didn't wreak havoc on the universe's first atoms while still leaving room for them to exist. While gravitinos remain purely theoretical, their potential influence reminds us just how fragile the early universe's chemistry might have been. One misstep, one overly energetic decay, and the atomic building blocks of everything we know could have looked radically different. It's a tantalizing what if that keeps scientists digging deeper into the laws that shaped our cosmic beginnings. Now, shifting gears to another fascinating possibility, let's talk about actions. These elusive particles, often floated as a leading dark matter candidate, might have played a surprising role in shaping the universe's first atoms. Unlike the disruptive gravitinos we just discussed, actions could have acted as subtle cosmic mediators, quietly influencing how atomic nuclei formed in those early moments. Actions are theorized to be incredibly light, nearly massless particles that interact only weakly with ordinary matter. But here's where it gets interesting. In the extreme heat of the early universe, actions might have facilitated nuclear reactions by acting as a sort of cosmic middleman. Picture them as invisible messengers, helping protons and neutrons communicate in ways that altered the rates of fusion or decay. This could explain why certain elements, like helium or deuterium, appear in slightly different abundances than standard models predict. Some theories even suggest actions could have temporarily stabilized unstable particles, giving them extra time to fuse into heavier nuclei before decaying. Others propose that action-driven interactions might have created tiny fluctuations in the primordial soup, seeding pockets where atoms clustered more densely, hinting at the large-scale structures we see today. Of course, actions remain hypothetical for now, but their potential fingerprints are everywhere. If they did influence nucleosynthesis, their ghostly presence could be hiding in the precise ratios of hydrogen, helium, and other light elements we observe. It's a delicate puzzle, one that keeps physicists hunting for actions in labs and cosmic data alike. After all, unlocking their secrets might just rewrite part of the story of how our universe's first atoms came to be. Now, let's venture into one of the more dramatic possibilities: primordial black holes. Imagine the universe in its earliest moments, a seething cauldron of energy where tiny black holes could have sprung into existence, not from collapsing stars, but directly from the chaos of the Big Bang itself. These minuscule cosmic traps, some no heavier than an asteroid, might have played a hidden role in shaping the first atoms by gobbling up matter before it could fuse into nuclei. Here's how it could have happened. In the dense, hot soup of the early universe, regions of slightly higher density might have collapsed under their own gravity, forming black holes on a microscopic scale. These primordial black holes wouldn't have lasted forever. Many would have evaporated over time due to Hawking radiation, but while they existed, they could have acted like cosmic vacuum cleaners, sucking up protons, neutrons, and other particles. This theft of matter would have left fewer ingredients available for nucleosynthesis, potentially altering the expected ratios of hydrogen, helium, and other light elements. Some theories suggest these black holes might have clustered in certain areas, creating patches of the universe where atoms were unusually scarce. Others propose that their gravitational pull could have stirred the primordial plasma, creating ripples that influenced where galaxies later formed. Even more intriguing is the idea that some of these tiny black holes might still lurk in the cosmos today, hiding in the dark corners of space, their presence betrayed only by subtle anomalies in the distribution of matter. Of course, primordial black holes remain speculative, but their potential impact is hard to ignore. If they existed, they could solve multiple cosmic puzzles at once, from the missing matter problem to the uneven distribution of galaxies. It's a wild idea, but in the quest to understand the universe's first atoms, even the wildest ideas deserve a closer look. Now, let's take a step into one of the most mind-bending possibilities. What if the rules of the universe weren't always the same? Picture this: the fine structure constant, which governs how atoms interact with light, or the strength of gravity itself, might not have been fixed in the early cosmos. If these fundamental constants were different even slightly, the entire playbook for atom formation would have been rewritten. Here's why this matters. The fine structure constant, for example, controls how tightly electrons bind to atomic nuclei. If it were stronger in the early universe, atoms might have formed more quickly or too tightly, altering the balance of hydrogen and helium. A weaker constant could have delayed atom formation entirely, leaving the cosmos in a chaotic plasma state for longer. Even tiny changes could have cascaded into massive differences, like a domino effect reshaping the periodic table before stars ever ignited. Some physicists speculate that these constants weren't just different, they might have evolved over time, shifting as the universe expanded and cooled. Imagine a cosmic dial slowly turning, adjusting the forces that dictate how matter behaves. This could explain why certain elements appear in unexpected abundances today, or why some regions of space seem to follow slightly different physics. Of course, testing this idea isn't easy. Scientists scour distant quasars for hints that light interacted differently billions of years ago, or study ancient meteorites for traces of altered nuclear decay rates. So far, the evidence is inconclusive, but the mere possibility keeps this theory alive. If true, it would mean the universe's first atoms were forged under rules we can barely imagine, rules that might still be hiding in the fabric of reality, waiting to be uncovered. Up next, we'll stretch our minds even further into the multiverse. Could our universe's atom ratios be just one possibility among infinite others? Stay tuned. Now, let's expand our perspective beyond a single universe into the staggering idea of the multiverse. What if the atoms we see around us, the precise ratios of hydrogen to helium, the delicate balance that allowed stars and galaxies to form, weren't the only possible outcome? What if they were just one roll of the cosmic dice in a sea of infinite universes, each with its own unique set of rules? This is the heart of the multiverse angle. In some versions of this theory, every possible variation of physical constants and initial conditions plays out in its own separate universe. One universe might have a stronger nuclear force, churning out heavier elements like carbon and oxygen right from the start. Another might have weaker gravity, preventing atoms from clumping into stars at all. Our universe, with its specific mix of hydrogen, helium, and trace lithium, could simply be the one where the numbers lined up just right for life to emerge. The multiverse idea isn't just wild speculation. It arises naturally from certain interpretations of quantum mechanics and cosmic inflation. If inflation never truly ends but keeps spawning new pocket universes, each could freeze into its own distinct physics. Some might be barren, with atoms that can't bond into molecules. Others could be so unstable they flicker out of existence instantly. Ours, it's the Goldilocks version, where atoms behave exactly as needed for complexity to arise. Critics argue this theory is untestable after all. How do you observe another universe? But proponents point to subtle clues, like unusual patterns in the cosmic microwave background that might hint at collisions with other bubbles. Others suggest that the very fine tuning of our universe's constants, down to absurdly precise levels, is indirect evidence that countless other combinations must exist. Whether the multiverse is real or not, it forces us to confront a humbling thought. The first atoms in our cosmos might not be special or inevitable. They could just be a single page in an endless library of cosmic possibilities. And that brings us to our next frontier. Could even our 3D reality be an illusion? The holographic principle awaits. Now, let's take a step into one of the most mind-bending ideas in modern physics, the holographic principle. What if the universe we perceive as three-dimensional, with atoms arranged in space, is actually a projection from a two-dimensional surface? Imagine the early cosmos not as a vast expanse of swirling particles, but as information etched on a distant boundary like a cosmic movie screen. This theory suggests that the first atoms might not have formed in the way we traditionally picture them. Instead, their configurations could have been dictated by data encoded on a 2D surface, translating into the 3D reality we observe. Think of it like a hologram where a flat image creates the illusion of depth. If this principle held true in the early universe, it would mean the distribution and behavior of hydrogen and helium weren't just random. They were constrained by the rules of a deeper, lower-dimensional reality. The implications are staggering. If atoms are projections, their properties, like mass, charge, or even the way they bonded, might have been written elsewhere. This could explain why certain ratios, like the abundance of hydrogen versus helium, appear so finely tuned. The holographic principle doesn't just challenge our understanding of space, it redefines how we think about matter itself. Critics argue that this idea is still speculative, with no direct experimental proof, but supporters point to black hole physics, where information seems to reside on the event horizon, not inside. If black holes obey holographic rules, why not the entire universe? Some even suggest that subtle anomalies in cosmic microwave background radiation could one day reveal this hidden 2D code. Whether the holographic principle holds the key to the first atoms or not, it forces us to ask, is our 3D reality just the surface of something far stranger? And if so, what other secrets about the universe's origins are waiting to be decoded? Next, we'll dive into another radical framework, loop quantum gravity, and how it reshapes the story of the cosmos. Now, shifting our perspective to another groundbreaking framework, let's explore loop quantum gravity and its radical reimagining of the early universe. Unlike the smooth, continuous spacetime of classical physics, this theory proposes that space and time are woven from tiny, indivisible loops. Think of it as a cosmic fabric made of threads rather than a blank sheet. If spacetime is pixelated at the smallest scales, how would that affect the formation of the first atoms? For one, the very conditions for nucleosynthesis, the process that forged hydrogen and helium, might have played out differently. In loop quantum gravity, the extreme density of the early universe could have been governed by quantum jumps in spacetime itself, altering how particles interacted. Picture a grid where energy and matter can't squeeze infinitely tight. Instead, they hit a fundamental limit like pixels on a screen. This quantum bounce might have prevented the singularities predicted by classical Big Bang models, offering a gentler birth for the cosmos. Critically, these discrete spacetime loops could have tweaked the rates of nuclear reactions. For example, the fusion of protons into helium relies on precise energy thresholds. If spacetime's granularity subtly shifted those energies, it might explain why we see slightly different abundances of light elements than standard models predict. Some researchers even suggest that loop quantum gravity's corrections could resolve puzzles like the Lithium Problem, where observed levels don't match expectations. Of course, this remains theoretical. No experiment has yet detected spacetime's pixelation, but the math reveals tantalizing possibilities. If loop quantum gravity is correct, the first atoms weren't just products of particle physics. They were shaped by the quantum architecture of reality itself. It's a reminder that the universe's infancy might hold clues not just in matter, but in the very fabric of existence. Next, we'll venture into string theory's hidden dimensions and how they might have left fingerprints on the cosmos's atomic blueprint. Now, let's stretch our imaginations even further into the realm of hidden dimensions. String theory, one of the most ambitious frameworks in physics, suggests that the universe might not have just the three dimensions of space and one of time we're familiar with. Instead, it could harbor tiny, curled-up dimensions too small for us to perceive directly. But if these extra dimensions existed in the early universe, how might they have shaped the very first atoms? Picture this: particles like protons and neutrons aren't just points but vibrating strings, with their properties determined by how they oscillate in these hidden dimensions. In the extreme heat of the cosmos's infancy, these vibrations could have influenced how particles interacted, altering the rates of nuclear reactions that forged hydrogen and helium. For instance, if certain string vibrations made protons slightly more or less stable, it could have shifted the balance of elements we see today. Some models even suggest that extra dimensions might have allowed fleeting interactions between ordinary matter and hypothetical particles like gravitons, leaving subtle fingerprints in the abundances of light elements. Here's where it gets even wilder. If these extra dimensions were unstable or collapsed as the universe cooled, they might have released energy that briefly turbocharged particle collisions, creating unexpected atomic configurations. Think of it like a cosmic pressure cooker, extra dimensions adding a burst of heat that tweaked the recipe for the universe's first atoms. Of course, like many grand theories, this remains speculative. No experiment has yet confirmed the existence of extra dimensions, but if string theory holds any truth, the atoms around us, and even inside us, might carry echoes of a higher dimensional past. It's a humbling thought. The building blocks of reality could be tied to geometries we can't even see. Next, we'll tackle one of the most provocative ideas of all, the simulation hypothesis. Could the universe's first atoms have been coded into existence? Now, let's take a step into the realm of pure speculation, where science meets science fiction. What if the universe's first atoms weren't born from natural processes at all, but were instead meticulously designed? This is the heart of the simulation hypothesis, the idea that our reality might be an advanced digital construct, and those primordial hydrogen and helium atoms. Just lines of code in a cosmic program. Think about it like this: the fine-tuning of the early universe's conditions, the exact balance of forces that allowed atoms to form, is almost suspiciously perfect. Too much gravity and everything would have collapsed into black holes. Too little and matter would have scattered into nothingness. Could this precision be evidence of intentional design? Some theorists argue that an ultra-advanced civilization, perhaps billions of years ahead of us, might have created this simulation as an experiment or even a form of entertainment. Here's where it gets even more mind-bending. If the first atoms were rendered by some kind of quantum computer, their properties might carry hidden signatures, glitches in the code. For instance, unexpected patterns in the cosmic microwave background or oddities in particle behavior could be clues, like pixels in a video game revealing the edges of the screen. Even the mysterious constants of nature, like the speed of light or the strength of gravity, might simply be default settings in this grand simulation. Of course, this idea sits firmly outside mainstream science for now. There's no way to test it definitively, and many physicists dismiss it as untestable philosophy. But it raises a fascinating question. If we ever did discover proof that our universe was programmed, would that make the atoms around us any less real? After all, even in a simulation, the rules would still shape everything we experience. So, as we wrap up our journey through these 30 theories, remember, whether you lean toward the rigor of Big Bang nucleosynthesis or the wild possibilities of simulated atoms, each idea reminds us how much there's left to explore. The universe's first atoms are more than just ancient history. They're the foundation of every story science has yet to tell. Which of these theories resonates with you? Drop your thoughts in the comments below, and don't forget to subscribe for more deep dives into the mysteries of the cosmos. Until next time, keep questioning, keep wondering, and keep looking up. From the fiery aftermath of the Big Bang to the mind-bending possibility of a programmed universe, we've journeyed through 30 wildly different ideas about how those first atoms came to be. Some, like hydrogen's dominance or helium's early abundance, are backed by rock-solid evidence. Others, like strange quark matter or simulated atoms, push the boundaries of imagination. But here's the beautiful thing: every single theory, whether mainstream or fringe, adds another piece to the puzzle of our cosmic origins. Think about it. Without those first atoms, there'd be no stars, no planets, no us. They're the silent architects of everything we see and know. And while we might not have all the answers yet, that's what makes this quest so thrilling. Science isn't just about facts, it's about curiosity, debate, and the courage to ask, what if? So now it's your turn. Which of these theories grabbed your attention the most? Was it the elegance of nucleosynthesis, the mystery of dark matter's role, or the sheer audacity of the simulation hypothesis? Drop your thoughts in the comments. I'd love to hear which idea sparks your imagination. And if you enjoyed this deep dive into the universe's atomic origins, don't forget to hit that subscribe button and ring the notification bell. There are plenty more cosmic mysteries to explore, and I'd hate for you to miss out. Until next time, keep looking up, keep questioning, and remember, the universe's greatest stories often start with the smallest beginnings.